Download this code from codegive.com, link in the description below. Off to the races, 3 ways to avoid race conditions in concurrent programming, with code examples. Race conditions are a notorious source of bugs in concurrent programs. They occur when multiple threads or processes access and manipulate shared resources simultaneously, leading to unpredictable and often incorrect results. The outcome depends on the unpredictable order in which the threads execute. Let's explore 3 common strategies for preventing race conditions, illustrated with Python examples. We'll focus on shared memory scenarios, as these are the most common source of race condition problems. Scenario: a shared counter. Imagine a simple counter that multiple threads increment. Without proper synchronization, the final value might be incorrect. This code will likely produce an incorrect final count because multiple threads are concurrently accessing and modifying counter. The plus equals operation isn't atomic, it's broken down into multiple steps: read, add, write, and if 2 threads try to do this simultaneously, one operation might overwrite the other, leading to a lost increment. 1. Mutexes, mutual exclusion. The lock and key approach. Mutexes provide exclusive access to a shared resource. Only one thread can hold the mutex at a time. Other threads trying to acquire the mutex will block until it's released. This prevents concurrent access and solves the race condition. The threading.lock creates a mutex. The with lock statement acquires the lock before accessing counter and automatically releases it afterwards. This guarantees that only one thread can modify counter at a time. 2. Semaphores, controlling concurrent access. Semaphores are a more general synchronization primitive. They manage a counter that represents the number of available resources. Threads can acquire, decrement, and release, increment, the semaphore's counter. If the counter is 0, threads attempting to acquire will block until a resource becomes available. A mutex is essentially a semaphore with a count of 1. Here, the semaphore ensures that only one thread can increment counter at a time. While functionally similar to the mutex in this example, semaphores are more versatile for controlling access to a limited number of resources, example allowing only 3 threads to access a database connection simultaneously. 3. Atomic operations *** built-in thread safety. Some operations are atomic, they are guaranteed to be executed as a single, indivisible unit. Python's threading.lock and threading.semaphore are implemented using lower-level atomic operations, but some programming languages or libraries offer atomic operations directly. If your programming language or library provides atomic increments, like interlocked increment in C or similar functions in other languages, you can use them to avoid the need for explicit locking. Unfortunately, Python's standard threading library doesn't have this feature directly for simple integer operations. You'd need a lower-level library like types to access such functionality, which complicates the code significantly and is usually overkill for simpler counter scenarios. Important considerations ***. Deadlocks *** improper use of locks can lead to deadlocks, where 2 or more threads are blocked indefinitely, waiting for each other to release resources. Careful design and ordering of lock acquisition are crucial to avoid this. Starvation *** one thread might repeatedly fail to acquire a lock, leading to starvation. Fair locks, not discussed here for brevity, can mitigate this. Performance overhead locking mechanisms introduce overhead. Overusing locks can significantly impact performance. Choose the appropriate synchronization strategy based on the needs of your application. Minimize the critical sections, code protected by locks, to reduce the performance penalty. By understanding and applying these techniques, you can effectively prevent race conditions and build robust, reliable concurrent programs. Remember that the choice of synchronization mechanism depends on the specific concurrency patterns and requirements of your application. Thorough testing is always essential to ensure the correctness of your concurrent code.